All right. Well, welcome to the October SJAA Imaging SIG. And tonight we have Bob Buchheim, who's going to tell us about, I guess I'd call it citizen science, but I'll let Bob describe it. You could see here a picture of Bob. He's the one on the right. He told me that a long time ago, these two kids dreamed of being astronomers. Neither one made it. The little guy on the right, after he grew up and had some disposable income, still wondered whether there was a way for amateurs to participate in astronomical research, and it turned out there were quite a few ways, enough to fill a book or two. So Bob wrote those two books, and he's going to tell us about them tonight. So please, Bob, take it away.
Thank you, Hi, and my other thank you is to Jim for inviting me. I hope I don't embarrass you with this. Okay, this is an imaging group. I bought my first CCD 20 years ago when a friend of mine got all excited about making asteroid position measurements. And since then, I've found the sciencey side of amateur astronomy to be pretty addictive. It's a little intimidating to be addressing a group of astro-imagers because I'm really only a dabbler in that field. And I can't make my slide go forward. There it is. This is, here's a picture of mine. I'd say that it's a halfway decent image, and I hope it'll give me at least a little bit of street cred in this imaging group. I've seen that many of you can do quite a bit better, but there's a story behind this image that I'll come to in 15 or 20 minutes. The important thing for tonight is that if you can make a halfway decent astro image, then you can do any of the things that I'm going to tell you about. The topic tonight is, can amateurs contribute to astronomical research? Now, obviously, we cannot compete with the professional astronomers because we live in two entirely different worlds. They're up there and we're down here. They have big glass, great skies, million-dollar instruments. They have PhDs, and they deal with telescope allocation committees. And that turns out to be a really big deal in the world of professional observational astronomy. Those big telescopes are oversubscribed. If you're the typical professional research astronomer, you might get 2, maybe 3 nights a year of observing time. And if it's cloudy on your night, well, you can always apply next year and try again. And if you have a project that needs to stay on that telescope and that telescope pointing at your object or objects all night, every night for a week or two, you can pretty well just forget it. Meanwhile, we're down here. Obviously, we have small telescopes, and that means that we're limited to bright objects. But it's worth remembering that the faintest object that we can observe is roughly the same brightness as the brightest object that they can measure. Otherwise, their instruments saturate. And we own our telescopes, and that means that our observing time is really limited by our enthusiasm and maybe our other personal schedules, but they're ours. If we want to spend a dozen nights on something that interests us, there's no allocation committee that says you shouldn't do that. It's a bad use of telescope time. Those two things mean that our competitive edge is small telescopes, bright objects, and telescope observing time that's flexible on our own schedules. So my plan is to see if I can entice some of you into that dark side of amateur astronomy, doing sciencey things. I'll spend about a half hour telling a few stories about how you can use your imaging equipment for discovery and for measurement. And then if any of this actually sparked some interest, we'll have plenty of time to discuss the details. Now, here's a really good image by Jay Gabaney, a fellow that I have admired for a long, long time. And I'm going to click my mouse and go on to another image that he made of this same object. Did you notice the difference? No.
No.
Okay, look here. And we zoom in on that. Here's the first image. And here's the second one. Two images taken some time apart and blinked is how Jay was not the discoverer, but these two guys, one in Germany and one in Sweden, were the discoverers of that nova near M27, just back quite a while ago. And they were using, modest amateur scale equipment, a C11, and I don't even remember what a comp star was. Old Starlight Express cameras. The deal was they took advantage of their observing time and they took the time to blink their images. Now, most of you take subs and sum them in order to get your deep images. Take the time to blink them. You never know what you might find in there. I remember, I think it was about 5 years ago, a fella down in South America was taking a picture of some galaxy, 5-minute subs for several hours, and he captured the initiation of a supernova. Never been done before, but he was in the right place at the right time. Now, if you're planning on making a discovery, of course, the odds are kind of against you. Your image field is pretty small. You're looking at a tiny fraction of the sky. You have no idea when the next event is going to pop off. So it's a low probability of success aspect of our hobby. But sometimes the universe conspires to dramatically increase your odds of participating in a discovery. And it turns out right now, this month, next month, and December are one of those times. Because sometime in the next 2 or 3 months, starting a few weeks ago, there will almost certainly be a nova in M31. Point your telescope and camera right there. The story is there's a recurrent nova. It's been observed, I think, 5 times now. Its recurrence time seems to be just about exactly 1 year, maybe 6 months. There's been some space-based X-ray stuff that said something was going on in the intervening, but of course, it's observable by us now. 6 months from now, it'll be behind the sun. Based on the last 2 or 3 outburst events, the current outburst is predicted for November 14th, give or take a month and a half. So the deal is start now, monitoring that area nightly or whenever you're out observing, and examine whether the eruption has begun. Your field will look like that. And what you're looking for is the reappearance of that star. How you do it is exactly the way you would take any other astro image. In this case, luminance, clear, unfiltered images are perfectly fine. You want to go deep. Your goal is to be able to reach magnitude 19 stars. But it's okay to stack subs to get an hour or 2 hours of equivalent shutter open time in order to do that. Pixel scale of 1 to 3 arc seconds is desirable in order to make sure that you're not getting flummoxed by a cosmic ray or something in there. But the real key is to take advantage of the fact that we have our own instruments. We can observe frequently, ideally every night. Take deep images of that part of M31 and examine that point in the sky to see if anything has changed. Our goal is to detect the eruption and notify the principal investigator that indeed it has begun. The PI, Matt Darnley, already has an array of big telescopes and space-based instruments ready to go on a target of opportunity basis when the eruption is confirmed. So if you decide to get on this and you know you go out one night and there's nothing there, and the next night and it looks like there is something there, send your discovery images, and probably one that was pre-discovery to me at oca_bob@yahoo.com. I'll pass them on to the PI along with your contact information, because you'll probably have some questions. And that will trigger the rest of the team, if they haven't seen it yet, to get on it and confirm the detection, and then get that array of large telescopes with their $1 million instruments to observe this thing. Once it is detected, our job isn't over. We need to do continuous, you know, every night, if possible, imaging of this thing after it's detected. Based on the prior eruptions, it'll probably be visible and measurable for us for 2-3 weeks after the initial eruption. And our images and photometry derived from them will be useful, because those big professional and space-based observations are likely to be snapshots in time. And our continuous record of photometry on a guy like this helps to put those in context, what was going on between those professional observations. So that's action item number 1 for you, M31, whenever you're out for the next month or so. Now, somebody said photometry, which is one of my favorite things, the science of measuring the brightness and color of objects in the sky. It's amazing the number of things that are in fact variable when you look at them. There's almost all of the astro-imaging programs that we use, Maxim, AstroArt, AIP for wind, they all have a photometry module. So you're not going to go out and need to buy new software. There's 2 fundamental concepts in your images that you're going to use for photometry. The first one is, even though you take an image and it's got your target in there, it's not just the target that you need to pay attention to. For your target, your photometry software, when you tickle the right keys, will put an aperture around that target, 2 or 3 rings. Inside the center ring, it'll add up all of the ADUs on all of the pixels in there. That tells you how much light came from the target object in that image. But of course, every one of those pixels also has skylight on it. And so the purpose of the donut is to enable it to estimate the brightness of the background sky in that area, so it can subtract that out. And that tells you the instrumental brightness of the target on that image. The thing is, that's a very arbitrary scale subject to a whole lot of badness. For example, if you double the exposure, you're going to get twice as much signal. Your ADU count's roughly going to double. And then if a little cloud comes by, you know, it's going to come down again. So fundamental concept number 1 is differential photometry. In addition to your target, you want to identify in that same image a star that is known to be constant in brightness and whose magnitude is known. Usually, you're going to want to have a third star so that you can be a check that your comparison star is indeed constant in brightness and not changing. But then you're having told it, here's my target, here's my comp star, here's the aperture sizes. That photometry routine will take a sequence of images and it'll do some math on each of them to give you a graph or table of numbers that is the brightness of your target in magnitudes versus time. And as they say, almost all of the popular image processing softwares will have a tool like this. So you don't worry about the math. It'll take care of that. Our job is to make good images, and then you put them into that photometry tool, set the measuring apertures around the target and the comparison star, make the measuring aperture, you know, not too big, not too small, just about right to capture all of the starlight and not too much of the skylight. tell it what the comparison star magnitude is, and push go. And the output will be a table or a graph of target brightness over time. Concept number 2 then is, what do we mean by good images for photometry? In general, well, absolutely. You have to pick your exposure so that the ADUs on your target and your comparison stars are within the linear range of your camera. And I'm guessing that most of you understand what I mean by linear range. No saturated pixels. Usually if you're using a 16-bit camera, you don't want the peak ADUs in any star image to be over about 50,000. If you have non-anti-blooming gates, maybe half that. And the processing you do is bias, dark, and flat, and that's it. No deconvolution, no sharpening, anything like that. And the other thing is, try for well-sampled point spread fractions. Don't have square stars where the star image is smaller than your pixel. Don't bin. Ideally, 3 or 4 pixels across the full width half max of your point spread function. An example like this might be a little bit of overkill, but you can see that you see the whole smooth point spread function. If you run a profile across the middle of it, you can reproduce the position and the intensity distribution of the star image. That's what you're looking for. And when you follow those rules, your images are going to look washed out, maybe a little fuzzy, not beautiful, but they're tailored for making accurate measurements, which is where the beauty of the science comes from. And here's an example of a straightforward project. UZ Sagitta is the target star in this image. There's a comparison and a check star. I took, I don't remember, 2-minute, 3-minute exposures all night for a few nights, ran it through the photometry routine to see if I could see the effect of that eclipsing binary star. When the little orange star passes in front of the big yellow one, the brightness of the system drops. And when it passes behind it, it drops a teeny amount when the faint star is occulted. And here's the kind of result that you get. This is a plot of brightness along the vertical axis and time, in effect, on the horizontal axis. The pink line is the observed magnitude difference between comparison 1 and comparison 5. The fact that it's a flat line means that indeed both of those stars were constant in brightness through the duration of this project. And then the blue line is the object, the target, minus comparison star 1. And you can see that it's constant in brightness, and then that occultation or eclipse happens and it gets faint. And this is not subtle. That's like 2 magnitudes of fading. And then it comes back up and it's flat again. And then you see the little divot when the faint star goes behind the bright. So you're seeing an eclipse going on in the far reaches of the universe. And one of the things that this allows you to do is to measure quite precisely the time of those eclipses. And then if you're into the science, you report that time of minimum light to somebody like the American Association of Variable Star Observers, who compiles reports from everybody who looked at any eclipsing binary star in the last 6 months, and makes that record available to professional astronomers. Now, why would they care about that? Because if these stars are going around each other, like the Earth goes around the sun, well, the eclipse is going to happen now and now and now, right? Tick, 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 once around. And if you believed your high school physics teacher, we understand gravity and we understand Keplerian targets, and these things are just going to happen, tick, tick, on a regular cycle. It turns out they don't. Because many of these eclipsing binary systems, there's something more going on than just a gravitational orbit. Indeed, on this particular star, UZ Sagitta, imagine that you've measured your eclipse and you looked at the ephemeris and you calculated when should it have happened. And the time you measured and the time it should have happened, well, if it happened right on schedule, the difference would be 0. If it happened a little early, then your observed minus calculated time would be a negative number, maybe a few minutes, maybe an hour. If it happened after the predicted time, it'd be a positive number. And if you strung measurements for many years that people had made of the O minus C, the observed minus calculated time difference, the error in the occurrence of this eclipse, if they were occurring right on time, that'd be a bunch of dots that'd make a flat line, 0. The error was always 0. It always happened right on time. And they'd probably be a little random errors and just because of our measurement uncertainties. Here's the observed minus calculated time over the last 70 years for UZ Sagittal. It's not a flat line. The eclipse, sometimes happens a little early, sometimes happens a little late, and the numbers, the peak to peak, it's sometimes 20 minutes early, sometimes 20 minutes late. Not a subtle thing. And if you try to fit a curve through those data points, it's pretty well fit by a sine curve with a period of about 47 years. Each one of those data points is somebody spent a night with this star and reported the observation of its eclipse. There's a probable cause for that kind of a sinusoidal variation in the timing of the eclipses. And that is that we're not looking at a binary system. We're looking at a system with 3 stars. There's a third star in there, widely separated in a 47-year orbit. It does not eclipse either of the center 2, but it tugs on them with its gravity. As it goes around, it pulls them to and fro by about 20 or 30 light minutes as it goes around. And that means that eclipse signal arrives either a little early or a little late to us. And so now you've not only discovered that invisible star, but you've learned something about it. It's something about its orbit, and you get a little hint of its mass. That's not the only possibility. A lot of these binary systems have magnetic interactions that make the eclipses come not on schedule. Some of them are exchanging mass between the 2 stars. Some of them, there's a vibrant stellar wind. The whole system is losing mass, and all of that affects the timing of these eclipses. So observed minus calculated times on eclipsing binaries is a straightforward imaging and photometry project that has a whole lot of value in the study of binary stars and stellar properties. But binary stars are not the only things going around out there. There's also the killer asteroids closer to home. And if we're going to defend ourselves against the killer asteroid, we need to know more about it than just that its trajectory is sending it in the way of the Earth. Our counterattack is going to depend on its composition, its size, and other properties like its rotation rate. And you can do the same sort of differential photometry. If you take got an asteroid in your field of view, yeah, it'll move a little bit relative to the stars over the course of a night. But all of those standard image processing programs can handle a moving target. And you can do differential photometry on that asteroid. And the deal with an asteroid is it's not round, and they're pretty much gray. They don't have any color or significant changes in surface brightness. So here's my asteroid. And as it spins, when you see it kind of edge on, it's going to be a little fainter because there's less surface area reflecting sunlight to you. And then it comes around and it's going to get brighter and fainter and brighter. So you expect that the brightness ought to change if it's rotating. Here's an example. This is real data from asteroid 755 Quintilla, son of a gun. It gets brighter and fainter and brighter and fainter. So that gives you a pretty strong hint that it's rotating, and the period of that that cycle is 4.55 hours. So that gives you a clue that, you know, this guy is going around once every 4.5 hours. And it turns out that that light curve contains a whole gang of additional information besides the rotation period. The delta magnitude from brightest to faintest gives you an idea of the aspect ratio. You know, how long is it versus, you know, how long is it versus how tall is it? If it was spherical, as it rotates, there wouldn't be any brightness change at all. So if you have a flat line, either it's not rotating or it has an aspect ratio of about 1:1. The shape of the light curve, the fact that the first minimum is fainter than the second minimum, and the fact that there's this little kind of inflection point going on here, those all encode information about the details of the shape of the object. And so there's and other things that you can learn from these light curves. The shape of the object thing is sort of amazing. It's not hard to imagine that if you knew that this was the shape of the asteroid, you could calculate its brightness as it went around. It turns out if you get a family of light curves from different apparitions, there's a mathematical method called light curve inversion that will create a mathematical 3D model of the shape of the asteroid just from the photometry that we can gather. So that's a good thing. The problem with light curve inversion is it's a shape, but it's a relative shape. You don't know, you know, how big is it? Is it, you know, 1 mile or 20 miles across? But if you're doing planetary imaging, you already have a high rate imager that you use for lucky imaging on planets. That same technology can be applied to a phenomenon called asteroid occultations. You know, the asteroids are kind of passing in front of the stars as they go through their orbits. And every now and then, there will be an accident where the asteroid passes right over a star. It's sort of the asteroid equivalent of a solar eclipse. And if you get advance word of that, and you put yourself in the path of totality, and you set your telescope up staring at the star, when the asteroid passes in front of the star, it'll blink out for a few seconds. You've got a video record of that now. You know how long the blink was. The orbit of that asteroid is well known, so the time of the blink is telling you the diameter of the asteroid divided by its velocity, and the orbit tells you its velocity. So you've just kind of observed a cross-section size of that asteroid. And if it's not just you, but it's you and a gang of other observers that have scattered themselves across the path of totality of that occultation, each of you gets a chord of what the, you know, what the dimension of the asteroid was observed from where you were located. And those can be knit together into a profile of the asteroid. Here's a well-observed profile of 135 Hertha, then you can clearly see it's got a sort of a bean shape to it. These were almost all made with 2-inch, 3-inch telescopes and video cameras back in 2008. Some of them were a camera behind a half of a binocular. It's that, you know, kind of crude of an imaging thing. You don't have to see the asteroid, because what you're looking for is where the star blinks to time it accurately. Now, this tells you the physical size of the asteroid in addition to its shape profile. You know, how many miles across is it? And remember, I mentioned this idea of light curve inversion. The two methods are really work together. Here's the light curve inversion model of Hertha, and here's the profile from occultations. Pretty good validation, one against the other. And so now you know the physical size, shape, and rotation period of that asteroid, and you're prepared to make your attack against it with some useful information. Double stars, visual double stars. We've all looked at them. You look in your eyepiece and at Albireo, and one's gold and one's blue, and they're beautiful. Not very many people have thought about measuring their positions relative to each other and measuring how that changes over the years. Turns out that's still a vibrant area of research. The method is in some ways shockingly simple. William Herschel invented it. In our world where you're doing imaging, turn your drive off for a minute, and the star will slide in the east-west direction. So record that, and now you know exactly which direction is east-west, and that tells you the exact direction of north-up in your image. And the rate of motion tells you, with a little calculating, exactly what your pixel scale is, how many arc seconds per pixel. And then you make your image of that double star. The primary is the center of your coordinate system, and you measure the position of the secondary as angle relative to north and separation in arc seconds. And you write that down, and you put a little paper in the Journal of Double Star Observations, which then gets picked up and entered into the Washington Double Star Catalog. And here's the kind of thing that come out of that. This is double star MLB 102. When it was first measured in 1906, the secondary was not quite 5 arc seconds away from the primary and almost due south. The next time it was measured was 12 years later, and it had moved. It had moved away. It was now 6 arc seconds, and position angle had rotated about 20 degrees. And then, as luck would have it in this business, nobody looked at it again until 2007, when I was working with some people that got excited about visual double stars. And so in 2007, I measured it. It was way over here. That begins to look like orbital motion. Now, it's about time for somebody to measure it again, and it probably needs another 100 years of getting measured once a decade to fill out what that orbit looks like. But, double stars, eclipsing binaries, and visual binaries are really the only way that we know stellar masses. Everything else is inferred from models. Eclipsing binaries are really the only way we know stellar sizes. Everything else comes from models, and a few that come from Chara doing interferometry. So there's real science in here. It's pretty, and it's kind of fun. Those of you who are planetary imagers, you know all about lucky imaging. This guy, 5, 6, 8 arc second separation, that works with conventional CCD imaging. But once you get down where the stars are separated by, 1, maybe 2 times the seeing disk, you can't measure them anymore. They're too close together. But use that lucky imaging concept that you use for planetary imaging, and you can separate and measure 1 arc second pairs and start to map out their orbits, which are likely to have shorter orbital periods. So do that. I promised I'd come back and tell you the story behind this guy. First, it's not a picture of a galaxy. It's a picture of that, which is known as optical transient OT 2019. You meet interesting people when you get involved in the sciencey stuff. The story of this image begins when a a professor at University of Colorado got a call from a friend of his who said, something's happened in M51 and we don't know what it is. And we're not sure that we can get enough telescope time to really characterize it. Do you suppose that some of your amateur friends might be able to see it? So he called Wayne Green. Wayne called Woody Sims, who called me, and we said, yeah, we'll give it a try anyhow. And we went out and imaged M51. I said, yeah, not only can we see it, but it's absolutely bright enough for us to do photometry on if we stack images for about an hour's worth of exposure. So he said, so do, and we did. And midway after the first couple of weeks, Woody said, he's got a 14-inch scope. I've got a 16. I was on an 11-inch at that time. And it was taking long exposures. And he said, our friend Stan has a 20-inch in New Mexico. So we twisted his arm to start taking nightly images of this guy also in 2 filters. And as a result, when the discovery paper was published in AppJ Letters, Wayne and Woody Forrest and Stan and Mark and I were all co-authors on the paper because the optical photometry that went into that paper, almost all of it was ours. So that answers the question, can an amateur astronomer make a real contribution to research in astronomy? Yeah. Now, I've obviously been selling you the sizzle in hopes that you'll get intrigued and buy the steak of doing this sciencey kind of amateur astronomy. If I've hit a spark, you're going to want to become familiar with these 2 fine organizations, the American Association of Variable Star Observers and the Society for Astronomical Sciences, where you can get education, training, experience, mentors, and start joining this community of small telescope scientists. Full disclosure, I'm on the board of both of those organizations. It's amazing what people are doing in their backyards to assist research astronomers. And of course, buy my books, please. Projects like these are a great way of learning astronomy by actually seeing the phenomena that you're learning about with your own images and your own data. You'll meet people that you probably never would run across in your ordinary life. And who knows, you may discover something, you may make an important contribution and push the boundaries of the unknown out a little further in astronomy. So if I've sparked any interest, it's time to start talking and see what you'd like to talk about.
All right, thanks very much. So please, anybody have some questions for Bob?
I put them all to sleep.
All right, I'll ask one just to get things started. So is the Vera Rubin telescope going to put you out of business?
That's what used to be the LSST.
Yeah.
No.
Yeah. For background, most of you probably know this, but there's for at least the southern hemisphere, there'll be an all sky picture taken more or less every night with a real big telescope and the data distributed to the world.
Yeah.
Sorry.
Yeah, actually at AAVSO meetings a year or so ago, we had a long drag out battle about that exact question and the answer is absolutely not. And there's several reasons. Go look at the specs on the Vera Rubin telescope. I think 16th magnitude is the brightest star that they can measure. We own the bright sky. And the other thing is, even with nightly images, if something is changing on a time scale of minutes or hours, you don't get it on a once a night image. Even UZ Sagita, its period is 2.2 days in round numbers. You can go a long time before you see an eclipse at all. And with a cadence of one shot per night or per every other night, you have no clue what the actual period of that is. You'd think that Sloan would have put the asteroid light curve people out of business, because it looks at the ecliptic every, what is it, 2 or 3 nights, and it can see asteroids down to really faint, but it can't measure them to really bright. But if that asteroid is spinning at 4-hour period, what'll happen is that nightly cadence will cause you to get a perfect light curve with a period of 2 or 3 nights, aliasing if you're a communications theory guy. And it turns out that's a problem that pestered planetary astronomers back in the days of film photometry, because they take images relatively infrequently, and the literature from that era is littered with really nice light curves of asteroids, but the periods are flat out wrong by factors of 2 or 3. And it's amateur observers now in the late 20th and early 21st century that got the right answer on those. And there's an important reason to have a good collection of correctly done asteroid light curves. There's a famous plot that I think Al Harris invented of the size, the physical size of the asteroid in kilometers and its orbital period. And there's a boundary where the orbital periods are never shorter than X. And the reason is asteroids mostly are not monolithic boulders. They're rubble piles. And if it spun faster, it'd break in two. So you wouldn't be seeing it today. And so just knowing orbital periods is telling you something important about the asteroid, and the statistics of orbital period of rotation periods is telling you something really important about the population. If you find an asteroid with a rotation period of, I don't know, 15, 30 minutes, look out, that guy's a solid rock. So no, they're not going to put us out of business there. And what they probably are going to do is generate an enormous number of follow-up requests, because they're going to see something happening and they're going to go, well, somebody with telescope time needs to stare at this for a while. So yeah, if anything, it's going to increase the opportunities for amateur contribution. So that's the party line.
Okay.
No, we're in Q&A. So.
Steve, you're not muted.
Oh, that's good.
Another question from the audience? I can keep going, but
sure, I can chime in.
Now and
you can probably mute, Steve.
Oh, I can do it.
If you want to.
Huh? Yeah, let me see.
Yeah.
If I think, yeah, I got it. Okay, go ahead.
Okay. Sorry, Steve. So I would be willing to wager that most of the people on the call are CMOS users versus CCD. And also, I think that most people are not using any of the programs that you mentioned. So I'm wondering if there's
is there a barrier there?
Kind of more, yeah. And I did some Googling while you were talking, and doesn't seem like there's a crisp introduction for, in the last 5 years, basically, right? When the technology has changed. There's a whole bunch of imaging programs now where there used to be only 2, and now we have, CMOS cameras of all flavors that are much less expensive than CCDs.
Yeah, there's two things. I'll admit I have to plead ignorance regarding the software that you all are using. I'd be curious to know what it is. But for all of the differences between CCD and CMOS, once you've characterized your CMOS imager, it can do fine photometry. There's a lot of, well, Jim knows Gary Walker. He's using CMOS cameras, doing great photometry.
A lot of work has gone into characterizing CMOS cameras, and there's no issues at all. The modern ASI cameras are very linear, have nice small pixels, so you can put them on a small scope and still have good resolution and all of that. So turns out CMOS is not a barrier at all.
Now tell me about the software problem or difference.
Well, Hi, you can probably chime in on KStars/Ecos. Does it have a photometry module or?
Not really. But I mean,
Okay.
I did some photometry a few months ago. The FIS files are fine that it generates, or that any of our programs generate. You get a pile
Okay.
of FIS files, and then I used what's it called, astro-image,
Astro-image J, yeah.
something
Yeah,
like it, which was
that's-
a pain,
That's
but
free and it's great.
Yeah.
yeah, okay. It was a
And there's
little
a-
complicated. It had a startup curve, but what doesn't, I guess.
Yeah. And
But,
even
yeah,
easier. I'm
Go
sorry,
ahead.
Hi.
No, go ahead.
I was just going to say, even easier is the web-based AAVSO tool that allows you to create light curves, and and there's quite a bit of information on their website, and lots of videos on YouTube on how to get started with VFOT. It's called.
So your CMOS camera will take good images, linear and well sampled, and then there are either free like AIJ or low cost like VFOT. You have to be an AAVSO member, but $85 a year, and AIP for WIN, which is a pretty capable astronomical image processing program, is now unlicensed. No dinero involved. So doing the photometry analysis, there are free options available.
Okay.
Yeah,
good.
like I say, I had a little project I gave myself to do a eclipsing star. I forget what it was. I looked it up on there's a website that tells you what's going to eclipse what, and at what time and all that. Yeah, it was, got a light curve. It was straight.
Show it.
Oh, it'd take me 10 minutes to find it. The one bone I'll pick about with what you said was that it was no 2 or 3 magnitudes. I mean, it was probably 0.05 magnitude or 0.02 magnitude. It was tiny. It was buried, but with enough data, I could pull it out. But are there really? I guess that's my question.
Yeah.
There
Yeah.
many
I don't remember
binaries that are a magnitude.
Yeah, they come in all flavors, like you've observed. If the eclipse is only very partial, just kissing each other, and then they're about equal brightness, yeah, there'll be a very small delta magnitude. Well, if you go to the AAVSO website, public access will take you to a I don't remember the name of it, but there's a search capability where you can say, I want to know eclipsing binaries in this constellation, something that's conveniently placed in the sky. And then it'll give you a list, and you can check what the delta magnitudes are, and pick a big one if that's what you're looking for. But on the other hand, think about it. You got a light curve that reliably observed a 0.05 magnitude change. That's pretty neat. You couldn't do that visually.
No way. Yeah.
And that's nowhere near the limit of what you can do with a small telescope and a electronic imager on a CCD or CMOS. Last year, a high school girl here in Gilbert contacted me, wanted to do a science fair project about exoplanets. And so she used my observatory to observe an exoplanet transit. You know, there's the star and the planet, you know, passes in front of it, and the starlight brightened by a little less than 1%, about 0.01 magnitude. Absolutely clean signals. She was able to get, I think, 3 transits over the course of a month, update the ephemeris to improve the estimate of the orbital period from what's currently in the literature, and got 3rd place at the science fair. You know, what's not to like about that?
Yeah, hey, I found it.
Talking
I have to show you this just for a second, just to show off my light curve, if I can figure out how I can share my screen.
While you're bringing that up, I also will say I haven't used it, but there is aperture photometry tool in PixInsight. So if you're PixInsight, you know, processor, there is a tool there.
There's a script.
Yeah, it's in the scripts. Yeah, thank you.
Anyway, so you see that? There it is.
Oh yeah, that's AIJ.
Yeah, so you could see it went from 0.95 to 0.93.5. But
Well,
there it is. Cool.
But is that really WASP 36b?
I think so.
Yeah.
That's an exoplanet, right?
Yeah.
Oh yeah, that's what I meant to say.
Yeah,
I'm
that's
sorry.
a characteristic
Oh,
exoplanet
you're right.
curve.
So
That's
that's what I
fabulous.
did
And it's a really nice light curve too.
Yeah, that's clean.
I did 2 of them. One, I hope this might have been the one with the, I can't swear to you this was the one with my telescope.
You know, that was what, a couple of percent light dip there in that exoplanet.
Yeah,
I
you're
mean-
right. You're right. I'm sorry, I got confused. I
So
was
you're
thinking exoplanets, not.
so you're the
binary.
only guy in this group who's actually observed a planet around a star other than the sun.
I don't know about that. There's Mars. It's in the sky every night.
Yeah, but it goes around the sun.
Oh, I see. Anyway, you're right. So I was thinking about exoplanets, and those are the things with really small dips.
Yeah.
You're saying binaries have much bigger dips.
Well, you know, some do, some don't, but
Okay.
Well, same thing with exoplanets. There are some exoplanets that are, yeah, and there's I'll have to find the link, but there's a website where you can actually see what the brightness change is and figure out if it's within the capacity of your instrument.
Right.
You can do a lot of exoplanets with, you know, a 5-inch refractor.
No, yeah, that was my experience. You
Yeah.
could. It was very noisy. This may have been, now that I'm thinking about it, this data may have been with the small 62-inch telescope in Arizona, which was what they let this class I was auditing use. But so it was but I did one with my 4-inch refractor.
yeah, and the sky is full of them. There, you'll never lack for targets.
Yeah, and if you want to, AIJ has a pretty significant learning curve, but if you want to do it even easier, there's a guy at NASA named Rob Zellum who created a program called Exoplanet Watch. And if you just Google Exoplanet Watch, you can find it. And he's wrote a Python script, and all you do is you take your series of images. So, you know, they generally ask you to take images for about an hour before the transit is expected and an hour after. So you go into the web-based tool and you find one that is, you know, while it's dark in your backyard, and you go and you take, you know, 100 images or, you know, whatever cadence you need to be able to get a quality image. And then you just dump that stack of images into his Python script with some darks and flats, and out comes a light curve out the other end.
That would be nice.
Yeah.
You know, everything we've talked about in the photometry world has been time series at a pretty rapid cadence. But don't forget, there are also stars like Betelgeuse that have pulsation periods measured in years, and there's everything in between. You know, there's Cepheid variables that, you know, might have a pulsation period of a few days. And so if you can't get out and stay out all night, there's still targets that need photometry on an appropriate cadence, which might be every night, might be once a month, in order to fill in the light curves. And again, a lot of them are outside the ability of the professional astronomy community to deal with. You know, all this stuff about Betelgeuse and the great dimming, the lion's share of the data came from backyard observers. Because, you know, you go to Mount Palomar and stare at Betelgeuse, you're going to melt something.
Yeah. Okay, I cheated. This is my data. Now you could see it's total noise, but if you time average the points, you get this.
Okay.
Yeah.
So there you go.
Yeah.
It's XO2B. So you're right. So that other image was with the 62-inch on top of a mountain, and it was a very beautiful light curve. And this is with a 4-inch, you know, from Silicon Valley.
Still, you know, 4-inch telescope,
Yeah.
observing a planet around another star. And obviously you can do this because remember the, what's it called? KELT, the kilodegree extremely little telescope. It's,
Yeah.
I think, what, 3 or 4-inch aperture, and they're searching for exoplanet transits with it.
Oh,
And their data looks really ratty.
now all I have to do is
Yeah, I'm
find the-
concerned with our natural sky or the light pollution that we get from Silicon Valley, especially the center of Silicon Valley, like where I am.
Mhm.
If that kind of noise can cover all the possible signal.
Well, obviously you're a little more limited than if you were in a nice dark place, but imagine differential photometry. You're kind of subtracting out the sky glow. The noise in the sky glow is still there, but the offset you subtract out, and you focus on targets that are bright enough that you get a good signal to noise ratio without saturating your image. Or, you get a little, there's a limit there, but you can still do productive work. Let me ask, raise your hands. How many of you have actually seen Algol go through an eclipse? Nobody? Well, there you go. You know, magnitude 2, right?
Well, and here's the other thing, Bob. You know, I live in downtown. I live in Nagley Park, right in the middle of downtown. I mean, the worst of the light pollution, right? I have no problem doing exoplanets with my 5-inch refractor.
Mm-hmm. Algol, by the way, everybody's heard of it. Turns out not very many people have seen it go through eclipse. I made a light curve of Algol Eclipse using a old Canon DSLR and its kit 50mm lens.
Yeah.
Just put it on a barn door mount, not even a telescope mount. And here's the thing. Remember I talked about timing the eclipses and then contributing the eclipse time to the record. If you look at the observed minus calculated time history of Algol, it's like the stock market. There are a lot of interactions going on in Algol. There are more than 2 stars in there. I think some people think there's 4 or 5. And there's some kind of either magnetic or wind interaction going on. There's a lot of physics happening up there that you need a continuous record of eclipse timings to keep track of it. And you can do that with really small, simple equipment from a horribly light polluted area.
Okay.
Try it. It's fun.
Yeah.
We all know about the primary eclipse that's, if you're diligent, is visible with your naked eye. There's a secondary eclipse, and you can see that in a DSLR light curve if it's carefully done.
Yeah.
Something that wasn't even discovered, I think, until the 1940s.
There's also, Bob, if you Google, there's an AAVSO seminar that was done by the woman in Florida, Barbara.
Barbara Harris.
Yeah, Barbara Harris. Thank you. And she talks about using your DSLR with just the lens on the camera to do the photometry. So if you want to get started and just try it with a regular camera, you can do that even without putting it on a scope.
Yeah, I didn't.
Sorry.
I didn't talk about filters at all, and you probably know that professional photometry uses a whole different set of filters, spectral prescriptions than tricolor imaging does. You know, you use RGB, the photometrists use BV and R and maybe I. But there are projects where, frankly, it doesn't matter because, like in the eclipsing binary time of minimum thing, all you're trying to see is the bottom of that curve, and the filtering can be useful, but it's not mandatory. If you've got your RGB filters, they can be made use of in these sciencey projects. So the message there is you don't necessarily have to go out and buy anything. Use the gear and the skills that you have and add some measurement to the processing of the images in addition to going into Photoshop and making them beautiful.
Yeah, the thing I wanted to add to Paolo's question was what I learned from that exoplanet transit project I did was that, you know, you can do it with light pollution, but what you trade off is time resolution. So, you know, you won't be able to make measurements, you know, accurate to the minute because you're going to need, you know, 20 minutes of exposure to get a good measure.
Yeah,
of
you get
flux.
a qualitative, not quantitative response.
Right.
Yes.
I'm just saying, so you won't be able to get these sharp curves because, well, that first thing that I showed earlier where it was just so noisy was my, you know, 30-second exposures of the star. And yeah, the stuff was all over the place. And then what I did was I took a moving average of those points and then I got the dip. And so, you know, of course I lost time resolution when I did that moving average. And so you can do stuff, but, you know, you won't be able to measure, you know, this happened in 10 minutes.
Yeah, exactly at that time. Yeah.
You know, and those kind of measurements are useful for, I don't know how big if you're trying to measure exactly how big the planet is, maybe that's nice.
And you know, in the eclipsing binary world, our friend Wayne Green a couple of years ago was doing a project with some student, and he couldn't find the eclipse. He looked at the ephemeris and said, by golly, you know, 12 o'clock tonight, it's gonna, and it wasn't there. And he roped me into helping. And it took us, I think, a week of nights to track down the O-C curve. The last eclipse timing was like 50 years ago. And the orbital period was off by, you know, a minute, but a minute per orbit times 50 years, you didn't even know what night the eclipse was going to happen on. And so, you know, you come along now and say, okay, I measured it tonight and my measurement is good to a minute. Well, shoot, you know, that is a gigantic improvement over the situation before you made that measurement.
So Bob, one thing you didn't talk about was time.
Yeah.
Time is important in these measurements. And, you know, of course, our place around the sun affects the timing of these eclipses and whatnot as well.
Yes, you need good accurate timing in your header, which means that you got to have good accurate time in the computer that's controlling the camera. I use Dimension 4. I think that's kind of become a de facto standard for a lot of people, but yeah, you want to have your computer clock right for most of these projects to a second, which isn't that hard.
No, it's not.
You know,
Now, the occultations that Bob talked about, though, those do require sub-second accuracy to be able to draw the shape of the asteroid. And
yeah,
what they do there is they essentially take a clock, a GPS clock, and put the clock in the frame of the image is one way that they go about it. And then there's one of the QHY cameras actually has a GPS clock built into the camera and specifically for doing those. But it just depends on the kind of science that you're trying to do, how accurate your time needs to be.
Makes sense.
One of the things about the asteroid occultation deal is you go to the website of the International Occultation Timing Association, which I think is occultations.org. Anyhow, if you Google IOTA, International Occultation Timing Association, they, with Gaia, they can make extraordinarily accurate predictions of the path of totality where the occultation is observable. And you can probably find one a month that's within easy driving distance for you. And it's kind of a kick to just, do a road trip to, stay in some field in the middle of the night to record an asteroid occultation. It's a whole different aspect of amateur astronomy. I spent a night in the middle of a dry stream bed in southern Baja.
I look for the opportunities when they're going to cross a rest area.
All right. Are there any more questions? All right. Well, I think we've probably exhausted our questions. That was really fascinating, Bob.
Well, thank you, guys. I hope I've seduced at least one or two of you into trying some of this.
Right. So can you, once again, just share your, how people get in touch with you? Just
yeah, I'll put my email in the chat here. So if you get out there and do some nightly imaging of M31, and you see that nova erupting, wave a flag and let me know, and I'll get you in touch with the PI.
All righty. Well, thank you very much. And unmute and
Yeah.
give a big round of applause. And
Thank you, guys.
we'll see everyone next month.
Thank you.
Thank you. Bye.
Bye.